All right. I don't see it. Just a minute. Just a minute. All right. Look at the see my screen now. All right. So the information that you know, if you get something similar to this, right? I want to just follow um, in terms of the information. So you get the column and thing like that. The column information, the height of the structure, what the partition width, which is a dead load, the live load, which is that as well, 40 PSF, pounds per square foot. The concrete strength is 4,000 psi. The steel strength is 60,000 psi. The span, right, which is this. Um, you could be asked possibly to do to calculate the span in one or two direction. Okay, all right. So if you're looking at the span in say two direction, the internal, you'd have to look at this, for instance, from here to here, and from on, and also from here to here. But if you're only looking at it from one direction, you would have to approach it internally and externally. All right. So note that one direction, you have to know in terms of the slab depth. Externally, as in when I say externally, I call this external, internal, external. All right. There are some conditions that are to be met in using this, and we'll get into it in terms of the loading and the span and how the how the columns are placed. All right. You want to calculate here um, deflection and shear force. I'm going to just rule out shear force and look at calculating the the moment that is on on a one direction on the slab, whether at the end or the column. So in a case like this, I think this calculation that I've uploaded only calculated the end, but in truth and in fact, you also need to calculate the middle as well in terms of applying the formula. All right. So in terms of deflection, I am going to go to a table, this table that it is referring to finding deflection. You don't know the height of the slab. And when I speak of the height of the slab, do you understand what I'm talking about? The depth of the slab, that's what I mean. Trying to see if I could get it in my thing there. I couldn't get it in something there. Let me see if I could. Oh, I can, Give me a minute. Let me just stop share 1 minute because I could have get it in. Yeah, you have it as a PDF, as an email. I was going to just copy it into my blackboard, my whiteboard. Okay, okay. Let me see. Okay, right. It will work. Where is it? I have it here. All right. Let me see if it's gonna work. Okay. All right. I think it will work. All right. I think it works. 1 minute. 1 minute. I need to get the table. Yeah, two tables. You okay? All right. The table. Where's the table? Where's the table? Where's the table? right. I'm just trying to pull up the table that I in reference to this. Yeah, it is the table that I want. I'm gonna show you the table. It's similar, but I think it has a little bit more information. The one that I want to use. Um, right, I'm gonna this. All right. Okay, 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 okay. Table two. That. All right. Let me. All right. Let me see. I'm going back to my screen. All right. Share. All right. You see my screen, right? All right. So these are the conditions to be met. Three or more span in each direction, variation, success. In terms of the span, right? So there is a criteria in terms of the adjacent span not to be more than a certain percentage. The live to dead load should not be greater than twice the dead load. The column offset must not be less greater than 10% in direction. The L over B, which is the length to breadth, should not be greater than 2 in terms of span. And this is when you have for beams, for slab and beams. This is the equation that you apply. All right. Um, so I want you to note something here. Depends, you can be given with job panel, without job panel. I think in this example that we showed, this example, let me just go to it. In this example, right here, right, um, when we come on to finding the height, right, the height of the structure, all right, we're talking about if you should do a cross section of the structure of a slab. It's too big. Just a minute. All right. All right. So it is just a cross section of the slab itself. All right. So you kind of want to find the, which is this distance, the height, in order to control deflection. So in essence, deflection is important there. This case, you see the ln is a clear, should I say the clear distance. What do I mean by the clear distance? In this case, because we were looking at it in this direction, the clear distance, cutting a cross section along here, cutting a cross section along here, right? And look at the slab that way. Basically, that's what you're looking at. The clear distances between here and here. All right. So the clear distance in terms of column is between here and here. Okay. So that is why we made mention of clear distance. How do you find the clear distance? In this case, it was 18. It was 18. So if you have 18 minus, we already know the area, the column dimension. We convert, because this is in feet, we convert all of this in feet by dividing by 12. We know that this was 12, the column was 16 by 16. So we say 16 by 16 on either side, because we're trying to find the distance between here, so a clear span. All right. So we actually get 16 feet, convert that by multiplying by that to get that. But remember, I want you to note this, that this deflection that we are finding is using the equation as is to find this, to find not that, where is it? So we were using without edge beams, all right, with edge beam interior panels. So in a case like this is important, where you know you find it the edge beam without edge beam, but you also have this internal as well to look at. Okay, to also look at as well. um I want you to note something here. So this is just this calculation was solely for the, again, for the edge, but there's also needs to calculate using 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 one of these equation based on the asterisk tells us that the strain that you're using, double asterisk, is 60 kips per square inch. So if it is 60 kips per square inch, that is for the internal. So you'd have done the external and then you move to the internal. All right. So in terms of approaching that, where is it? Okay. All right. So when we did the clear distance, which is, this is supposed to be in inch divided by 30, you get this. So you round it up, you get 7. If you were doing 33 internally, just for argument's sake, um, this would be what? This would still correct. So it would be 200 divided by 33 for the internal. Well, let me see what anybody work that? What would that be? 33 divided by,
6.06, sir.
so so this is equal to 6.06. Ooh, interesting. In this case, you could take the chance and round it down here. Does that become 1? Yeah. Yeah. All right. But if you do, I mean, it's similar. I mean, if you round it up, it's just that this is rounded off. This more closer to 6. So you'd have to find what the internal deflection information given on this. All right, so we move on from, okay, let me just, this is doing a shear check. Um, I don't think I need to get into the shear. What I need to get into, okay, another important information is that whatever the deflection of the slab is, it has to be greater than 5. Sorry, it has to be greater than 5. So if you get something less than 5, then you have to use 5, basically. If something is less than 5, all right. Um, this this also deals with the, okay. Let me just go and get into this. All right. I think what is important here is the factor. After you find the deflection, is to find the factor dead load. All right. The factored dead load, right, is the self weight. Did I calculate the self? How do I calculate the self weight? Let me get back to this. So how do you calculate the self weight? There are some assumptions that will be made, right? If you're not given, you could make the assumption in terms of, if you have, well, this is for share check, so I don't think the assumption is needed if you're not doing a share check here. But if you're doing a share check, then you need to ensure that the average effective depth, right, equal to h. You have to stipulate, if some information are not given, you have to basically, because you're designing, you have to make some assumption, basically. So the h, we already established h, which is 7. The cover, and we're saying the cover is 3 3 and the rebar is half inch. After you remove that, anything from the, well, it's normally, yeah, I'm not sure, they're kind of conservative here. Normally is the center of the rebar. All right, so you could divide that by 2 minus that, and you get the center of that. All right. Um, no, I think even though I said divide by 2, no, don't divide by 2, because you're dealing with 2 layers of steel. Then in essence, it's actually zero point 0.5, if you understand what I'm saying. All right. So you do 2 layers of steel, one on top and one on bottom, basically. Um, the slab weight. How do you calculate the slab weight? The density of concrete is 150 psf. That is an important information to note, right? Already convert that, the depth of the slab, right, into inches. I mean, into feet, because you have it in inches. You get 87.5. So therefore, the this case, I guess this was checking to find out from the perspective of shear if the 7 inches is okay. In this case, it is okay. All right. So the next thing, from finding the deflection, have to find the factor dead load. So the factor dead load, right, is 1.2, which is a factor. The self weight of the, which you just got, which is 87.5. The 20, where do you get the 20 from? You have gotten the 20 from the information given earlier, which is the partition weight, which is a dead weight. So that is a dead weight of the structure. Then you carry out you carry out the multiplication of that. You get that after you apply the factor. The factor, you're going to factor the live load. What is the factor of the live load? You already gotten the live load, basically. Yeah, you factor that, which is 1.6. You got that. Then you have basically the total factored load, right, which is dead load, live load, 29. That you got that. So you're going to investigate. Um, this is if you're carrying out shear. If you're carrying out shear, you're going to be investigating for beam action, right? 12 inches away from the strip of a distance d. We already established d, and so on. All right, so
Question. Do you
yeah,
assume that BW?
say that again.
Do you assume the BW? Because you said that the BW equal 12 inches. That wasn't
Yeah,
given.
yeah. So the BW is 12 inches from the when you're dealing with the wide strip action where the shear would take place. So you can safely make that assumption.
So, sir, early in up top, you said we don't need shear. So, is this a part that we do have to calculate, or is it a part that is needed?
If you're asked to calculate shear, certainly yes.
So, with the exam, would it be asking if should we calculate shear, sir?
No, we're not going to get into shear.
All right, sir.
All right, so just in case you ask, but yeah, for this purpose, no. So you check that two-way shear action. All right, that is that. All right, so I need to get to the important meat of the matter, which is all right. So this is where check for the directional design method. You carry out your check in terms of the number of span. Three, long to short span is less than two-way, then fine. Columns are not offset. You do your checks to make sure you record the checks. Loads are uniformly distributed as seen in terms of dead load. The ratio of the dead load, which is the live load is 40. The dead load is that plus that equal. So it is basically less than twice, okay, the dead load. So therefore that is okay. Slab is without beam. Factored moment. What is important? This formula is important. This formula is important. All right. So we already find the the loading factor. This what I calculated was where is it? Which is this? What is being converted to keep because it was pounds. So everything converted to keep here. We already know in terms of the yeah, we know what was the clear span. We know what is the L sub two, which is basically perpendicular to ln, the clear, and then we got for the moment in the slab we got 93. Okay, so the total factor moment distribution per slab into the negative and positive moment, then into the column and middle strip, and that's what we're going to do now in terms of applying. This is what we're going to apply. How do we apply this? Um, the Where is it? All right, is it this? Yeah. All right. So in applying that, yeah. Let me get back to the
Excuse me, sir. Would that table be given in the
yeah table like that would be given. Um, Let me see now. Uh, where is it? No. Okay. Oh, see it here. All right. So the interior negative, which you, where is it? So this is it basically. So the interior negative. So the total moment that you have gotten, then the strip, then the middle strip. So the column strip, the middle strip. So let's go back. All right. So we know what 22 point, yeah, I've gotten it right there, right? to, let me see something here. 1 minute. Okay. All right. Yeah. All right. So basically, the negative, the exterior negative is 0.26 multiplied by the load, the moment that you'd have gotten, and that basically applies itself right across the positive, the interior negative. So basically, you're moving inward based on how you cut, based on how the direction of the slab that you're dealing with. Meaning, let me go back to this. So if you're looking at this, so you look at this, I mean negative, right? Then you look at the interior, then you look at that. What this table doesn't have, right? Let me show you something. So this table, so we have negative, so we have the exterior negative, which is the exterior negative. Where's the exterior negative? So this is the exterior negative, which is one here, exterior negative, which is here. So that's why we have the 26. Then we have the positive, right? So where's the positive? So the positive is here, which is 2. Then we move to the first interior, right? Then we have the interior positive, all right? Then we have um, the exterior, the interior negative as well. So a positive, negative. So, but if you have, but in this case, let me show you something. Where is it, man? Where is it? Okay. That. In this case, you have this. If you understand what I'm saying. So you have negative, positive, negative interior, positive interior, negative interior, and so on. So you would have to take that into consideration in applying this table. Okay. So we see negative, positive, interior negative. All right. And the interior negative may be a case where the span may vary. Okay. All right. Then we move. So you see all of this. Then we move to positive. So we have the interior, oh, see it here. So we have the interior span. All right. So the interior span, where is it? Okay. Which is this. So this is the interior. Okay. This is the interior negative. So in this case, we have interior, right? Well, based on this, it would have another thing there, which basically go back to the end. All right. So it would actually an end span basically. So this replicate itself over on this other side, if you understand what I'm saying. All right. After you have completed that, so this is one if it's a case where that, but this was us dealing with the edge, right? In essence, what you're trying to do is to see the worst case scenario, because if you do another deflection from where we have started, which is this deflection here, right? If this deflection is of the importance in terms of finding your thickness of your slab, which ultimately affects the self weight. of the structure. Um, let me see if it gonna affect anything else. Um, let me just double check on something here. Yeah, it will affect this self weight of the structure. So you'd have to find that for the interior, for the interior slabs, meaning. So you did the edge, but there's this interior as well. You can safely say if the dimension are the same, then it's going to replicate itself the same here. But this may vary in terms of the deflection because what you're going to find out is that deflection internally, right, given from this, if you don't have an edge, is this equation depends on the length. Okay, but in that case the one that we use at the edge was that, or this was it. No, not this one, sorry. I was incorrect when I said edge. It is actually this 36. All right. No, this is with Japan. No. Oh, sorry. Yeah, this. Let me get the 33. Interior panel, which is this. Mhm. Yeah, and it's based on the asterisk in terms of the the shares the PSI. All right. So go through that. Try to understand that. The the um the other thing that you need to go through, which I think you kind of have a fair understanding, is the portal frame and cantilever and the cantilever method. And that would be a two-story. Let me tell you, so can you say that it's a two-story, and just brace yourself if you have gotten in terms of the cantilever the area of each column. All right, the area of each column. All right. Um, so go through that. There is a understand the distribution of the load on slab and how it goes to the beam. Have an idea of how you would calculate bending moment. Okay. Um, what would be good if you, I know there are different persons who employ a different method regarding back to the moment, back to the portal method and the cantilever method. I'm asking that you, when a question like any of those questions, summarize your axial, your reactive force, as in, summarize it in a table form, um, and so forth. That in terms of, that is good in terms of summation, especially when you use a different method from what we have looked at. Uh, the shear force information that I've sent you, yeah, there's no equation given on shear force, but you can go through that and so forth. All right. Um, I guess if there's no other question, I guess that's it for tonight. And I can only wish and pray your very best.